Hey everybody, welcome back. We are jumping into our first lecture related to the performance-based liquefaction hazard analysis crash course. And in order to understand what we're doing with performance-based liquefaction hazard analysis, we have to understand some basic building block parts of the problem. And one of the foundational parts of the problem is understanding how we predict ground motions. And why is that? Because predicting ground motions leads to our predicting the seismic loading that contributes to the problem of liquefaction in the first place. So, to understand how to predict ground motions, it's necessary that you understand some basic stuff about what ground motions are. So that's what we're going to walk through for the next few minutes. All of this material is taken from lectures from my 545 graduate level geotechnical earthquake engineering class. And if anything here doesn't make sense, or if you want to learn more, you're welcome to hop over to those series of lectures on my YouTube channel, and you'll find everything you need over there. All right. But we're just going to do basically a crash course in this content here. So what are you looking at in this picture? You are looking at a ground motion recording, but this is no ordinary ground motion recording. This is the first ground motion recording. This is the famous El Centro record, recorded in the 1940s in California, and it was the first ground motion record that was recorded in the world. And that's a significant deal, because prior to this event, earthquakes had always been viewed by mankind as some superstitious phenomenon, the gods must be angry at us kind of thing, and it was something that was to be feared. It was like the boogeyman. After this event, where we recorded the ground motion, that's where science stepped in and said, okay, how can we understand this motion? Why did this motion occur? Why does it look like this? Why was it not smaller? Why was it not bigger? Why was it this duration? And all of these questions that we could ask from this record led to where we are today in the field of earthquake engineering. And so it really is a monumental feat to have this ground motion record. And we now have tens of thousands, if not hundreds of thousands, of recorded ground motions, because earthquakes happen all over the world every single day. And so now we have these records. So let's go back to this question that I have listed here at the bottom. So you've recorded an earthquake. You have this time history. Now what? How are you going to quantify this? How are you going to describe this time history using just a few numbers? This leads us to the topic of ground motion parameters, or GMPEs, that they're often called, GMPEs. Ground motion parameters. A ground motion parameter is a metric to quantify or describe a ground motion numerically with numbers. So we've learned, or if you take my class, you will learn that there are three aspects or contributing components that we have to consider if we want to describe an earthquake ground motion. And these are, first, the amplitude of the earthquake. So if I have a time history record where this is the amplitude and this is time, and the record, is doing its thing, the amplitude defines basically how high the record is on the plot. So it's a measure of the intensity of the ground motion time history. Now the second is the frequency content. The frequency content, this describes essentially the period or the rate at which these waves are coming in. And this is significant because different frequencies of ground motions cause resonance with certain frequencies of response mechanisms. And the most basic example of this is the famous opera singer holding a wine glass example. She can flick the wine glass and she can listen to the tone that glass is vibrating at. And if she can produce a sound that matches perfectly that frequency and increase the amplitude of her voice at that frequency, you'll see the wine glass break and shatter. It's actually really hard to do, but a few people have done it, and so it demonstrates the concept of the importance of the frequency content. Now, the third aspect of a ground motion that we can describe is the duration, or the length or the time of the ground motion. So how long the ground motion is occurring. So these are the three significant components to describing an earthquake ground motion, and ground motion parameters either fall into one or more of these bins of amplitude, frequency content, and or duration. So here's some examples of various ground motion parameters that we can measure today and the bins that they fit within. Everything from the peak ground acceleration. This is the big one we use for liquefaction, and it's the easiest of the ground motion parameters as well. But you can see some frequency parameters, you can see some duration parameters, and then there's a few parameters that fall into multiple bins. For instance, the areas intensity. This measures the area underneath the curve of the acceleration time history. So it's like an integral of a squared value. And so what you're doing is you're measuring the energy produced by that particular time history. So that is a function of the amplitude, the frequency, and the duration of the earthquake. So some of these parameters, cumulative absolute velocity is very similar to the areas intensity. It's also measuring the area beneath the curve of the time history. And so these ground motion parameters are often called, what's the term? Evolutionary ground motion parameters, I think is what they're called. And I'm not sure the term for that or why we call that, because I think a lot of scientists and engineers are wanting to move away from the silos of amplitude, frequency, or duration and move more towards these parameters that consider all of the silos simultaneously. So maybe someday we'll actually move in that direction. So if we can record ground motions from actual earthquakes and we have metrics to describe their intensity using ground motions, but what do we want to do, or what can we do if we want to predict ground motion parameters from an earthquake that hasn't happened yet? So this is where we get into the development of what are called ground motion prediction equations, or GMPEs. These commonly used to be called attenuation relationships, but few professionals refer to them as attenuation relationships anymore because it's such a vague term. No one knows what is attenuating. But when you talk about GMPEs, then everyone knows you're referring to ground motions. So for a few decades now, seismologists have been developing ground motion prediction equations from recorded time histories. What they do is they take a recorded time history, they know the location of the instrument that recorded the earthquake, and they know the location of the fault that ruptured. So they can calculate the distance between the instrument and the fault. Knowing that distance from the source, they can take that recorded time history and quantify whatever ground motion parameter they want from that time history. And let's just for example, let's say we're looking at peak ground acceleration. So a seismologist can take a whole bunch of earthquake time histories, and knowing the distance of those instruments to the earthquake sources, they can plot the PGAs of the earthquakes from those time histories versus the known distance from the source. And you might see, if you were to do that, that seismologist would see a trend that would look like this, where we see large PGAs at short distances, and we see lower PGAs at further distances from the source. That's why they used to call these types of relationships attenuation relationships, because the ground motion parameter would attenuate with distance from the earthquake. So whenever you see a bunch of dots like this, what do you always want to do? If you're like me, at least, you can't help yourself, right? You need to fit a curve to those dots. It just makes the world feel much more balanced and at peace. And so as you fit a curve to these dots, this right here is the GMPE. And that's a relationship now that we can say for some future earthquake, if I know a distance, say r star, if I know a distance from my site to some seismic source, I can predict what that ground motion parameter from that seismic source would be. By the way, this GMPE, it's a function of the earthquake magnitude. So if I had a different magnitude I was looking at, I'd probably have a different GMPE. So every magnitude shifts according to every GMPE shifts according to the earthquake magnitude. But we're just looking at one magnitude right now, and therefore we get one peak ground acceleration. So these initial GMPEs, the very first ones that were built, were just based on earthquake magnitude and that source to site distance. But since that time, GMPEs have become much more sophisticated and more complex as researchers continue to look for ways to minimize this scatter of the data. So you can see how all this data is scattered around my best fit line. And so there's uncertainty with my prediction. But if I can process this data and filter it and add more complexity and more variables in an attempt to try to tighten up that data around my relationship, then I have more confidence in my ability to predict the ground motion from that future earthquake. So what do modern ground motion prediction equations look like? Well, rather than just magnitude and source to site distance, they look at things like the fault type, the geometry of the fault, whether it's a hanging wall or a foot wall. They account for local site effects like site response. They account for basin effects. They count whether you're dealing with the main shock of the earthquake or potential aftershocks, and other factors go into these equations. So these aren't just simple functions. These things are monsters, and they're very difficult to compute and use by hand. And so most engineers and seismologists today use computer programs that have these GMPEs programmed into them already. Now, ideally, every geographic area that experiences earthquakes would have its own set of ground motion prediction relationships. And I could ask the question, why? Why is that? Well, the reason is, if I'm only looking at data that's local to the site that I'm interested in, the scatter in that data is going to be much less. A lot of that scatter we see in these GMPEs comes from the fact that they're coming from different seismic environments, different types of rock, different types of faults, different types of soil on top of the rock from all over the world. So if I'm only focusing on the same region, I eliminate the variability in the different types of rock, the different types of soil, the different types of seismic sources. So a lot of that scatter gets eliminated. The downside of that, though, is if I'm only focusing on earthquakes from a specific region, then I'm also eliminating a ton of my data points. I can only use data that comes from that specific region. So we can't produce these site-specific ground motion prediction equations for places other than those that have a lot of earthquakes. And the reason for that, as I mentioned, is because we don't have enough recorded earthquakes over the span that we've understood these things. But we're recording earthquakes every day. And eventually, over time, we're going to arrive at this point where we can have site-specific attenuation relationships, or GMPEs, for every place in the world. Right now, for instance, there's a lot of site-specific GMPEs for places like Christchurch, New Zealand, because there was an entire smorgasbord of earthquakes that happened there in 2010 and 2011 and since that time. But other places aren't as fortunate, or maybe I say unfortunate, to have as many earthquakes to provide data for the development of site-specific GMPEs. So, what do we do for places that don't have a lot of recorded earthquakes? Well, you don't really have a choice then, do you? You have to start combining recorded earthquakes from other parts of the world that did experience earthquakes. So when you start taking earthquake records that are from geographically different areas, with the assumption that the ground motions from those areas are similar to the ground motions that you'll experience in your area, you're applying what's called the ergodic assumption. And this assumption has been shown to not really hold. I mean, there are differences between different seismic environments, but it's the best we can do. And we live with the error that's introduced from applying this ergodic assumption for now. But in the future, like I said, someday we'll all be relying on site-specific GMPEs. So what GMPEs do we use today? In the western United States and other areas throughout the world that are recognized as high to moderate seismicity, most professionals, engineers, and seismologists use what are called the next generation attenuation relationships, or the NGAs. Now, the NGA was a giant project where numerous seismologists prior to the NGA project were just working independently, and they each had their own little databases of ground motions, and they would produce their own models based on their own beliefs and their own assumptions. But the problem was that there was a lot of conflict between these seismologists, and they didn't agree on a lot of things, and it left a lot of confusion for professionals going, which model should I choose? Which model is right? Which model is wrong? So the NGA project sought to acknowledge that everybody can have a different opinion and still produce a valid model. So the NGA project brought all these different seismologists to the same table, and they all developed and were given the same set of ground motion recording data, and they all agreed upon it. They didn't change it or modify it. Now, they could use it or they could throw it out, but they couldn't change the data. And so of the data that was being used, it was the same data among everybody. So with this effort then, and by the way, don't be fooled. What I'm describing sounds really great, but it was a major, major effort. 5 separate research teams were given the same set of ground motion data, and they were asked to develop GMPEs to fit to that data. The first iteration of NGA was published in 2008, But then immediately after that, a second iteration of NGA was initiated, and those models were completed and published in 2013 and 14, and they were called NGA West 2. So NGA West infers that these are coming from the western United States, or areas of high seismicity, and the 2 means it's the second iteration of NGA. So here are the different authors of those various relationships, as you can see here, and many of these authors are just legends in the field. So all of these relationships, by the way, were published in the publication Earthquake Spectra from EERI. So some of you may ask, why in the world did they need to do a second iteration of the ground motion prediction equations? They completed one set in 2008. Why in the world did they start a second iteration? Well, here's why. So in the original data that they were using for the first NGA West project is shown here. We see earthquake magnitude versus the source to site distance. And each of these blue dots represents an earthquake event that the teams had ground motion data for. Then, after 2008, we had earthquakes in Peru, in Chile, in Haiti, in Japan, in New Zealand, all within about a 2-year period. I mean, major earthquakes. So within a 2-year period, our number of dots grew from that to this. Oh, I'm sorry. Gosh, I'm getting all this mixed up. I'm sorry. This plot right here is before NGA. This plot right here is the plot that was given to the NGA West 1 teams. So you can see that there's not a ton of difference between that database and the pre-NGA databases that a lot of people were using. Then, here we go. Then, after 2008, and between 2008 and 2011, this happened. I still laugh out loud when I look at that. We had tons of data that filled in holes all over this plot. And these areas that I'm circling are areas where we had lots of gaps and holes. So NGA West 2 gave us a beautiful gift in terms of smaller moment magnitude at farther distances, smaller moment magnitudes at shorter distances, very large moment magnitudes at large distances, and then it filled in a few of these gaps here in some of the moderate earthquakes as well. So yeah, it was definitely warranted. And so today, most engineers and seismologists use the NGA West 2 ground motion prediction equations, including the U.S. Geological Survey. What about the areas that aren't the western United States? So this is like the central and the eastern portions of the United States. Well, those NGA equations that we just talked about, they don't apply to areas of low seismicity or continental seismicity. And before the introduction of, traditionally, the seismologists and engineers applied a very complex recipe of numerous ground motion prediction equations, all of them weighted differently, to try to predict continental sources. And why would that be? Why have such a complicated recipe? Well, it's because, my friends, there was a ton of, I can't spell. There was a ton of uncertainty. We didn't have a lot of historical ground motions in these low seismicity areas by definition. So it was difficult for us to predict any future events in these areas and have confidence in those predictions. But around the same time, the same group of seismologists was also asked to develop NGA equations for continental seismic sources. And that's called NGA East. And in NGA East, or the NGA East report was released in 2014. However, those models are still undergoing peer review. They still haven't been published in the seismology literature. So as of July and August 2021, these models are still being peer reviewed and they're not published. But it's getting close. So for example, the summary of the database that was used by these model developers was published in July of 2021 by Goulet and others in Earthquake Spectra. And so I suspect that the NGA East ground motion prediction equations will not be far behind, the peer-reviewed ones. To help you understand what is in NGA East, this comes from the summary report that I mentioned. So this figure on the left is a diagram of all of the earthquake events that were used to build the NGA East database. And you can see, the maximum magnitude is like a 6, but it goes all the way to magnitude 3s. We have earthquakes from Oklahoma that represent instances of induced seismicity from fracking and injecting deep water deep into the bedrock. And a few of these other ones, like there's the Richmond, Virginia earthquake that rattled a lot of the East Coast several years ago. And here on the right figure is the similar plot I showed before, where we have earthquake magnitude versus source to site distance. So again, you can see lots of holes here, right? Lots of holes. And those holes are probably going to stay for a long time, because we're talking about a region where we don't have a lot of natural seismicity because they're continental regions. But the good news is that the U.S. Geological Survey is holding off on releasing its most recent update to the National Seismic Hazard Maps and its seismic source model for mapping. These are the ground motions that we use in building code, by the way. It's holding off on those because it's waiting for these peer-reviewed papers to get released. So yes, the most recent version of the USGS mapping did incorporate this NGA East, these NGA East models. What about subduction zones, you may be wondering? I'll just give you verbally a very quick update. NGA has also been working on the NGA subduction project. So they've been developing ground motion prediction equations that are specific to subduction zone sources, so like Cascadia or subduction zones all around the Pacific Rim and in the Mediterranean Sea. These are the seismic sources that can produce the massive earthquakes, like the one that produced the 2004 Indian Ocean tsunami, or the earthquakes along the coast of Chile and Peru that are these massive 8.5, 9.5 earthquakes. So those models have also been developed, and a report has been provided by NGA, but those papers have not yet been peer-reviewed and published. All right, that wraps up this lesson, and in the next lesson I'm going to talk about how engineers and seismologists can take now these GMPEs and use them to predict future earthquakes from real seismic sources that exist all around us at our various sites. So I hope that you'll join me and come back for that next part of this interesting lecture series. Thank you so much for your attention, and have a great day.